Well, hello again, ladies and gentlemen. So let's move on and finish off our chapter on entropy by investigating the concept of isentropic efficiency. This is a way for comparing or calculating the efficiency of an actual device that may contain all sorts of irreversibilities. So the idea here is to calculate the maximum possible work that a device can produce, let's say, and then use the isentropic efficiency to calculate the actual work produced. So we calculate the maximum possible work a device can produce, and then we can calculate the actual work that a device that has irreversibilities in it. We calculate the actual work by using what's called the isentropic efficiency. Isentropic efficiency is basically a work or a power divided by a maximum work or power. Okay, that's the way we understand efficiencies. We'll talk about this in a moment. So we'll define isentropic efficiency for a work-producing device, a turbine. So remember, turbines are work-producing. And we'll also calculate or derive an expression for isentropic efficiency for a compressor, which is a work-consuming device. And then we'll do an example involving isentropic efficiency for a turbine. We'll do an example today showing you how to use isentropic efficiency to calculate the actual work or power produced by a real turbine, one that contains all sorts of irreversibilities, okay? Okay, so let's get started here. Let's say we have two turbines. Well, actually, let's say we have a real turbine. So let's say we have a turbine. Okay, so we have some sort of a turbine. Now this turbine receives a certain inflow of something. Who knows what it is? Could be air, could be H2O. And so there is a propeller in here, and it's producing a certain amount of work output. So this is work turbine or work turb. So this thing is producing some work. Now, let's say this turbine is adiabatic. So no heat transfer. Okay? And this turbine also is not only adiabatic, but it may contain irreversibilities. So there may be some entropy being generated inside. So this guy is not reversible. Not reversible. So there's some S gen going on inside. So this means S dot gen is greater than 0. So there's friction in there. Who knows? There's friction in there. What else is going on? Who knows? Now, if you apply the entropy balance to this thing, and it's steady state, let's say, you will find that S dot gen is equal to m dot times S out minus S in. If you apply the entropy balance, there's no heat transfer, so the Q dot over T interaction goes away. If it's a steady flow device, the dSCV dt goes away. It's a single inlet, single outlet, so the summations go away on the m dot S terms. You take the S dot gen, you put it over on the left-hand side, and you get m dot S out minus S in. Or if you like, S out minus S in is equal to S dot gen over the mass flow rate for the working fluid. Okay? So if I draw the TS diagram for this device here, TS, let's say the inlet pressure, I've got an inlet pressure P1, I got an inlet temperature T1. I have an outlet pressure P2 and an outlet temperature T1. Of course, I have specific entropy too. I have S1 and I have S2. Okay, so I have inlet and outlet properties. Presumably this turbine is decompressing, so pressure is falling in the turbine, and so is temperature falling because I'm extracting work. So we have two isobars here. See, we have P1 and we have P2. And I may have a T1 here. So the inlet state, this is the inlet state number 1. And of course, I have an inlet specific entropy, S1. And then I decompress down to a pressure P2 and a temperature T2. So this is state 2 right here. And this is S2. So temperature falls. I extract some of the energy in the form of work. There's some irreversibilities inside. So entropy, specific entropy, also goes up. So this delta S from the inlet to the outlet is S dot gen divided by M dot for the working fluid. So the process looks something like this. For the air as it flows from the inlet to the outlet of my turbine. Okay? So that's what the process looks like for the non-reversible adiabatic turbine. Delta S is positive as we go from the inlet to the outlet because of entropy generation. Now let's do the same thing for the reversible turbine. Let's do the same thing for the reversible turbine. So this will be W dot turb, and I'm going to put reversible REV in the superscript. So this is reversible turbine. So this is the inlet, this is the outlet, and so we have a P1, T1, and an S1. We have a T2, a P2, and an S2. Okay, this is the reversible turbine. It's also adiabatic. It's also adiabatic. Now, if I apply the entropy balance to my reversible turbine, adiabatic, steady state, I get the same equation. I get M dot S out minus S in is equal to S dot gen. Now, if it's reversible, that means that S dot gen, no entropy generation, so S dot gen is equal to 0 if it's reversible. So S dot gen is 0. So this implies S out equals S in, or S2 is equal to S1. So on the TS diagram for the reversible turbine, here's our two isobars here. P1 and P2 are the same as for my regular device. We're going across the same delta P. Same delta P. Note, delta P is equal to P1 minus P2 is same for both turbines. Okay, same delta P, same inlet temperature too. I got a T1. So here's T1. Here's my state 1 right there. And because it's an isentropic process, so S out is equal to S in, so this is isentropic. It's isentropic expansion in the turbine. Pressure's falling, so it's expansion. And so the process looks like this. So here is state 2 down at the bottom. So here's T2, and here's S1 equals S2. So that's what the process looks like for the reversible turbine. Vertically downward, state 1 to state 2. By the way, this state 2 is kind of a special state. It's the state for an isentropic expansion. So I'm going to put a little s right after the subscript 2. I'm going to put a little s here. And I'm going to call this state 2 sub s. So this is going to be 2 sub s. And I'm going to put a circle around it. 2 sub s means for the constant entropy process. So this sub s means constant s. Constant s. Specific entropy. S1 is equal to S2 sub s. Okay? Now the question is, which device produces more work? The turbine or the reversible turbine? Which devices are the most efficient? Devices with all sorts of irreversibilities or reversible devices? Well, the answer is, so let's make a little space for myself here. The answer is W dot turb is less than the work produced. So the work produced by the real turbine is less than the work produced by the reversible turbine. So the reversible turbine is the most efficient. So this allows me to develop an expression for efficiency. Eta isentropic, so this means isentropic, turbine, T-U-R-B, is equal to the work or power produced by the actual turbine divided by the maximum possible, which is from a reversible turbine. So the isentropic efficiency for a work-producing device, a turbine, is W dot turbine over W dot reversible turbine. Needless to say, the value for efficiency, note, eta isen turbine, needless to say, the efficiency for isentropic efficiency for a turbine is equal or less than 1. If the efficiency is 100% or 1, we've got a reversible turbine. If the efficiency is less, we have an irreversible turbine. Okay, so let's write this one more time. Let's write this out one more time. So, review. The isentropic efficiency for a turbine is defined to be equal to the power produced by the turbine divided by the power produced by the equivalent reversible turbine, where P1, P2, and T1 are the same for the actual and reversible turbines. We have to start off with the same temperature and have the same pressure drop, else it's not fair comparing the two turbines. We're comparing a real-world turbine that operates between two pressure limits with the same inlet pressure with the maximum possible work produced by a reversible turbine. The TS diagram for both devices superimposed on the same plot. Temperature, S, same two pressure limits. P1, P2, they both start off at the same temperature, T1. The isentropic device goes from state 1 to 2 sub S. The real device goes from state 1 to 2. So S1 is equal to S2 sub S. That's for the isentropic device. And the real device ends up at S2. Okay? So this is how you compare the two devices on a TS diagram. One is reversible, one is not. And the isentropic efficiency is defined as the ratio of the work or powers produced. One last little thing. Two last little things. Note, we can also rewrite this efficiency in terms of specific work by dividing by the m dot of the flow through the turbine. So I can also write eta is equal to W dot turbine over W dot reversible turbine. I can write that as the specific work of the turbine times the m dot divided by the specific work of the reversible turbine times m dot. I guess I should have said here m dot is also the same. So P1, P2, T1, m dot are all the same. So the m dots cancel and I get efficiency, isentropic efficiency is equal to the ratio of the specific works. Okay, that's if I don't know what the m dot is, okay? Needless to say, another note, if eta isen turbine equals 1, then the actual turbine is a reversible turbine. Actual turbine is reversible. Okay? In general, eta, isentropic efficiency will be less than 1. It can never be greater than 1 because no device is more efficient than a reversible device. Okay? The same thing can be done with a compressor. I'm not going to go through the whole comparison. Suffice to say that a compressor is a work-consuming device. Suffice to say that a compressor is a work-consuming device, and the reversible device, or reversible compressor, will consume the least work to pressurize the flow from one pressure to another. So the reversible compressor is the power-consuming device which consumes the least power between two pressure limits. So we can go through the same thing for a compressor, but we end up with different definitions and a slightly different TS diagram. So for a compressor, so this will be a work or power consuming device. A compressor is meant to pressurize flow. So I have a certain inlet pressure, temperature, a certain m dot, and of course, needless to say, a certain entropy, specific entropy. And then I have an outlet, temperature, pressure P2, an m dot, same m dot, and an outlet entropy, S2. And I've got a propeller in here, or some sort of a, so this is, we're doing work. So we have W dot compressor here. Again, I'm assuming an adiabatic compressor. The power consumed by the actual compressor compared to the reversible compressor is going to be greater. So the actual compressor, which has all sorts of irreversibilities, friction, unrestrained expansion, who knows what else is going on in there, will always consume more power to get to the same pressure for same T1, P2 minus P1, or if you like, delta P, and for the same m dot. So for the same mass flow, the same pressure rise, the same inlet temperature, the reversible compressor will always consume less power than the irreversible compressor, the real, actual compressor, okay? So we're going to define the isentropic efficiency for a compressor as the compressor power for the reversible device divided by the compressor power for the actual device. The actual device consumes more power to pressurize the flow. Therefore, the denominator is greater than the numerator. So this guy is always less than or equal to 1. Okay? If eta Isen compressor is equal to 1, then the actual compressor is a reversible compressor. So I put a little box around this and note that this ratio, so definition of isentropic efficiency for a compressor is always less than 1, equal or less than 1. And if eta Isen, if it is equal to 1, that implies the actual compressor is reversible. Reversible compressor. Okay? Let's draw the TS diagrams for the reversible and the irreversible or actual compressor. TS. Same two pressure limits. So we're going from P1 to P2. So pressure is going up as we compress. That's what a compressor does. Pressurizes the flow. Let's see here. So state 1 is right here. So the compressor, both the reversible and the real compressor, start off at the same temperature T1 and the same pressure P1. And of course, we have an S1 right here. The isentropic, i.e. least work consuming device, goes from 1 to 2 sub S. That's the isentropic or reversible path. And the real device goes from 1 to 2. 'State 2 has a greater specific entropy than 1. So S2 is greater than S1 for the irreversible actual compressor. So let's go over this again. We have two compressors. We have a real compressor, which is what we're interested in, and we have a theoretical isentropic compressor, which consumes the minimum work to pressurize what I'm trying to pressurize. The isentropic device moves vertically up on the TS diagram to get from P1 to P2. The real device has entropy generation occurring, and therefore S2 is greater than S1. Delta S from 1 to 2 is going to be positive, and it follows a path which is not vertical, but it's some sort of an angle from state 1 to state 2 with a resulting increase in entropy from the inlet to the outlet because there's some entropy generation inside. The real device consumes the most power to pressurize the flow. The reversible device consumes the least power. So we take the ratio of the two and we call it the isentropic efficiency. If your isentropic efficiency for some device is 1, it necessarily means that the device is a reversible device, reversible compressor, okay? Isentropic efficiency, the ratio of the compressible work for the reversible compressor to the real work for the actual device, that's for a compressor, and it is the opposite, it's the inverse for the turbine. The definition, I'm going to put a little box around this. The definition for the isentropic efficiency for a turbine is equal to W dot for the actual turbine divided by W dot for the reversible turbine. The reversible turbine produces the most power. The actual turbine produces the least power. So this ratio here is less than or equal to 1. Okay, so put a box around these definitions for isentropic efficiency. Now, this isentropic efficiency is actually used in a lot of places. If you go to work for Pratt & Whitney, Rolls-Royce, GE, and you go into their compressor and turbine divisions and start working on their jet engines or power systems, you're going to be dealing with calculating, estimating, using isentropic efficiencies to try to estimate the actual efficiency of your turbine or compressor that's inside your jet engine compared to the maximum possible or minimum possible works or powers for the isentropic or reversible devices. So the isentropic efficiency is a way to characterize how efficient your turbines and compressors are. Presumably, as an engineer, you want to get isentropic efficiencies that are as close to 1 as possible. A well-designed turbine or compressor will have isentropic efficiencies typically around 70, 80, probably not 90%. But as an engineer, you want to get your isentropic efficiencies as high as possible. A well-designed turbine or compressor has isentropic efficiencies somewhere north of 80%. That's a well-designed compressor or turbine. 80% or so north of that is considered good for a real-world device with all of its irreversibilities inside. Okay? All right, let's have a look at an example here. We have an adiabatic turbine that received air. So this is an adiabatic air turbine. So this is air is the working fluid. So we have air coming in at 1200 degrees and a pressure of 800 kPa. So we have 1200 degrees Kelvin and T1 is 800 kPa. And the outlet pressure, outlet pressure is 400 kPa. So pressure falls as we go through the turbine. So P2 is 400 kPa. And as a result of the pressure falling, this turbine extracts work. W dot turbine is a work-producing device. The isentropic efficiency for this turbine, which is defined to be W dot turbine over W dot isen turbine, is 86%. So this device produces 86% of the maximum possible device. W dot isen turbine for a adiabatic turbine is the maximum possible work. So this thing produces 86% of the maximum possible work. that you could produce with this pressure drop at this inlet temperature. 1200 degrees and a pressure drop of 400 kPa. So what are we supposed to find here? We're supposed to find the specific turbine work, or if you like, W turb, which is W dot turb divided by M dot. We don't have any mass flow rates in this problem, so we can only find specific turbine work. And I also want to find the exit temperature T2. So I want to find the exit temperature T2. How hot is the exhaust coming out of this thing? Okay. Let me put up a TS diagram so we can kind of keep track of what we're doing here. Let's put up a TS diagram. TS. Let's put in our two isobars. So we have our P1 and we have our P2 isobar. So pressure is falling. State 1. So here's state 1. So I start off at a temperature T1 with a corresponding S1. The isentropic turbine moves vertically downwards to a state 2 sub S. And the real turbine has some presumably entropy generation. After all, it doesn't produce it only produces 86% of the maximum possible work. So there's going to be some entropy generation inside of here. So the real device is going to have a positive delta S from state 1 to state 2. So we're going to have a positive delta S from 1 to 2. So the real device goes from 1 to 2 with an increase in entropy. The reversible device, which produces the maximum possible work, moves vertically downwards. Now notice that the real device has a hotter exit temperature than the reversible device. So this is T2 and this is T2 sub S. T2 sub S is lower than T2 because we're not extracting from the regular device, we're not extracting the maximum possible power or energy from the flow. So the real device has a hotter exit temperature than the reversible device. So I'll just write this right here. Note, T2 is greater than T2 sub S. Why? Because W dot turbine is less than W dot from the reversible turbine. The reversible turbine is extracting more energy from the flow and producing more work, so the temperature is falling further for the reversible turbine. Okay? We're going to be calculating T2, and we'll probably calculate T2 sub S as well. Okay, T2 sub S. So I'm going to be putting some numbers in here. Needless to say, no, not needless to say, we're going to do this problem assuming constant specific heats. The previous problem we did involving entropy generation that was a nozzle, that was variable specific heat. So maybe we should do a constant specific heat problem here. Okay, we're not going to use any of these S naughts. Okay, so let's have an assumption section and then we shall get started, okay? Okay, so I want to find the work or specific work of the real turbine analysis. So I want to find the real work or the work for the actual device. If we write down the definition of isentropic efficiency for a turbine, not a compressor, a turbine, we get W dot turbine divided by W dot Isentropic, okay? Reversible or isentropic turbine. Now, I have the isentropic turbine efficiency as 86%. And I want actually I don't want W dot turbine. I want the specific work. Oh, well, okay, I guess we need to massage this a little bit. So W dot turbine is the specific work of the turbine times M dot for the air going through the turbine, divided by W for the isentropic turbine times M dot. The M dots cancel out. That's the definition of isentropic efficiency. Okay, so I want to get W turbine. So this means W turbine is equal to the isentropic turbine efficiency times the specific work of the isentropic turbine. I know the isentropic efficiency. I do not know the specific work for the isentropic turbine, W isenturbine. So I need to find that. Well, how do I find this? Well, let's apply the energy balance to my isentropic turbine. So by the way, this is our system here, both for the isentropic as well as the real turbine. So obviously it's an open system. So let's apply the energy balance to my isentropic device. E balance on the isentropic turbine. So this isentropic turbine, well, let's write out the energy balance. So we got Q dot minus W dot is equal to dE CV dt plus the sum of M dot H plus PE plus KE summed over all outlets. And then I got the same thing summed over all inlets, okay? Now this is an adiabatic turbine, so this is 0. There's only one form of work, and that's turbine work, or shaft work if you call. So this is W dot shaft. So it's producing shaft work. That's what the turbine's doing. It's got a propeller in there. No change in energy within the turbine. It's steady state. And I don't have any information. Well, let's have a look. I don't seem to have any information on any changes in height or any change in flow velocity at the inlet and the outlet. All I have are temperatures and pressures. I got no flow areas. I have no M dot. So I am going to neglect the kinetic energy and the potential energy terms. So I'm going to write delta PE equals delta KE equals 0. Also, I'm going to say steady state as well. So this is steady state. We're told that it's adiabatic, so I don't need to put that down. So that's gone, and these are gone. And I get W dot and I'm going to call this W dot shaft. I'm going to call it turbine work. And it's also for the isentropic turbine. So I'm going to get, I guess I'll write it right here. W dot isenturbine. There's only shaft work, and it's by the isentropic turbine. So I'll call it W dot isentropic turbine. So I get W dot isenturbine is equal to M dot H1 minus H2. If I divide by M dot, I get the specific work. W isenturbine is equal to H1 minus H2. And if I assume constant specific heat, I get CV T1 minus T2. Okay, oops, CP, sorry, CP. Cp T1 minus T2. I have temperature T1. Okay, I got temperature T1. I don't have temperature T2. By the way, this temperature T2 here and H2, let's go back to our TS diagram. Is this right? Remember, we're working on the isentropic turbine. State 2 for the isentropic turbine is actually 2 sub S. 2 sub S. That means isentropic. So I am going to put a sub S on all the 2's here. So put a little S here and put a little S here. Okay? Isentropic. S1 equals S2 sub S. Okay, getting a little bit compressed there. That's what that's for. Again, look at your TS diagram. For the isentropic device, we're going from state 1 to state 2 sub S vertically down, and S1 is equal to S2 sub S. Okay, so I need to find T2 sub S. Process 1 to 2 sub S is isentropic. So that's isentropic expansion in the turbine, the reversible isentropic adiabatic turbine. 1 to 2 sub S is vertically down, so S1 is equal to S2 sub S. So I can go, for constant specific heats, I can go to a property relationship. Let's have a look. Let's see if I can pull out a property relationship for constant specific heats. Okay, here. Oh, we don't need these anymore, or at least not for a moment. Let's see if we can find that table that contains, what is it, 6.2? Ah, there it is. I think that's it. Yes, table 6.2. Isentropic processes. Variable specific heat, there's the S naught stuff. Constant specific heat. T final over T initial is equal to pressure final over pressure initial, K minus 1 over K. Let's use this. Let's use this to calculate T2 sub S. Let's use this to calculate T2 sub S. T2 sub S over T1 is equal to P2 over P1, K minus 1 over K. And that's from the constant specific heat isentropic property relationship. To do this, I need K, the ratio of Cp over Cv. So I guess I need to look up some specific heats here. I am told to evaluate Cp and specific heat at 1,000 degrees. So let's see if we can find, in our table. Let's go here to specific heats for air, IGB, property tables. Cp and K for air. This is table B10. I only go up to 1,000 degrees, that's why I did it at 1,000. I see K is 1.336. So I'm going to write, never mind, Cp and K evaluated at 1,000 degrees Kelvin. I think I'll write right over here. K evaluated at 1,000 degrees Kelvin. What was it, 1.337? 1.336, 1.336. 1.336. Oh, do I have the right camera on? Let's have a look. I need to turn off the share. So K at 1,000 degrees is 1.336. K evaluated at 1,000 degrees Kelvin is 1.336. And that's from table B11, B10. All right, let's calculate T2 sub S. Let's see, that's going to be equal to T1 times P2 over P1, K minus 1 over K. T1 is 1,200 degrees, and my pressures are 800 and 400, as I recall. So T1 is 1,200, and the pressures are 800 and 400 kPa. Pressure drops through the compressor as we're extracting energy. So 1,200 degrees Kelvin, and then I have P2, which is 400, and I have P1, which is 800 kPa. The units cancel out. And then I have 1.336 minus 1 divided by 1.336. And I find a T2 sub S. T2 sub S is 1,008 degrees Kelvin. 1,008 degrees Kelvin. So let's go over here to my TS diagram, and I can actually put some temperatures in here. Maybe one temperature. So this T2 sub S. So this is 1,008, and this is going to be in Kelvin. So this is T2 sub S, 1,008 degrees, okay? Presumably the real turbine, which has irreversibilities, won't get all the way down to 1,008. It's going to be somewhat hotter because it won't extract all the same energy, okay? Okay, so now I have T2 sub S. Great. So, oh, I need CP. Oh boy. CP. Well, remember we're going to evaluate CP at 1,000 degrees, so I guess I better look that up. (1,000 degrees for air, 1.142. 1.142 kilojoule per kilogram to green Kelvin. So CP at 1,000 degrees, 1.142 kilojoule per kilogram to green Kelvin. And that again is from table B10. From table B10. Let's make sure I got the right one. Yeah, 1.142. Okay, great. Check. Okay, 1.142 kilojoule per kilogram to green Kelvin. Temperature T1 is 1,200 degrees, and T2 sub S is 1,008 Kelvin. The Kelvins cancel out, and I get kilojoule per kilogram, and I get the isentropic work for the turbine is 219.3 kilojoules per kilogram. 219.3 kilojoules per kilogram. So the isentropic turbine extracted out 219 kilojoules per kilogram of flow. So now I got the specific work produced by the isentropic turbine. 86% isentropic efficiency, 219.3 kilojoules per kilogram, and I get the work of the real turbine. the work of the real turbine is equal to 188.5. 188.5 kilojoules per kilogram. 188.5 kilojoules per kilogram. Okay, so let's write these results down. The specific work produced by the actual turbine, irreversible turbine, is 188.5 kilojoules per kilogram of airflow. Note, the reversible device, the one that produces the maximum possible work between the same pressure limits, W Isen turbine, is 219.3 kilojoules per kilogram. So W turbine is less than the isentropic turbine work. The real turbine produces less power than the isentropic turbine. Let's calculate the actual outlet temperature. The actual outlet temperature for the real turbine T2. We've already calculated T2 sub S. What was that? 1,008 degrees. Let's calculate T2. Let's apply the energy balance to the real turbine. Actual turbine. So I apply the energy balance, steady state, no heat transfer, single inlet, single outlet, no changes in kinetic and potential energy, and I get W dot turbine is equal to M dot H2 minus H1. Let's make sure these subscripts are right. H2 minus H1. So for the real device, we're going from state 1 to state 2. The isentropic device was 1 to 2 sub S. That's why in the energy balance for the isentropic device, at state 2, I had a 2 sub S. But the real turbine goes from 1 to 2. And of course, this implies W turbine is equal to H2 minus H1, which is CP T2 minus T1. Now, I have W for the turbine. It's 188 kilojoule per kilogram. I have a specific heat, and I also have T1, so I can solve for T2. So T2 is equal to T1 minus, let's see here. No. Yes. So let's see here. W turbine. Oh, I think I forgot the negative sign here. I did. There is a negative sign right there. Forgot the negative sign from the first law. Sorry about that. Let's see. So I get T2 is equal to T1 minus W turbine over, over CP. So divide both sides by CP. Take the T1 over on the left-hand side of the equation and flip the equation. And I get T2 is equal to T1 minus W dot turbine over CP. Okay? All right, now I have W dot turbine, I have CP, and I have T1. Let's plug in. Let's see here. T1 is 1200 degrees Kelvin. Minus W turbine, 188.5 kilojoule per kilogram. CP, we already looked CP up. What was that? Oh, what was CP? I guess I erased it. That was 1.142 kilojoule per kilogram to green Kelvin. 1.142 kilojoule per kilogram degree in Kelvin. The kilojoules and the kilograms cancel out, and the degree Kelvin goes on top. And I have, let's crank it out. Let's see here, 188.5 divided by 1.142. And I get 1,034 degrees. Actually 35 degrees Kelvin. 1,035 degrees Kelvin. So T2, 1,035 degrees Kelvin, box it up. Let's put this on our TS diagram. So T2 sub S was 1,008 degrees, and T2 is 1,035 degrees. So notice the real turbine has a hotter outlet exhaust temperature. Why? Because W dot for the real turbine is less than W dot for the most efficient isentropic turbine. Therefore, the outlet energy or enthalpy is going to be higher for the real turbine than the isentropic one, simply because less power is being extracted. In theory, I don't mean to get extreme here, in theory, if the real device is so irreversible, I'm guessing its isentropic efficiency were 0, then in theory, the outlet temperature could be equal to the inlet temperature if it's not extracting any work. So for an extreme case would be a turbine with an isentropic efficiency of 0. It produces no power. The outlet temperature, T2, would be equal to the inlet temperature, T1. Not much of a turbine, but is definitely an illustration of an extreme example. An extreme and a generality that real turbines will have a hotter exhaust temperature than a isentropic turbine. Okay, you could do the same thing with a compressor for this kind of a problem. So you'd have a different definition of isentropic efficiency for a compressor. You would still be applying the energy balance. You would still be looking at an isentropic process, 1 to 2 sub S, to get a isentropic compressor work. So compressor problems are very similar to turbine problems, except that you're going up the TS diagram. You're starting here and you're going up. You're increasing pressure, and your definition of isentropic efficiency is flipped, okay? Similar sort of problem involving a compressor. You'll see examples of isentropic turbines and compressors in your notes and in the textbook. All right, take care, ladies and gentlemen.